Welcome to this last screencast on arrays and array lists. Basically, we'll be talking about multi-dimensional arrays. So the idea is we can create a two-dimensional array with two pairs of square brackets. So we say int array, second dimension array A. So we have now a two-dimensional array. The first pair is the number of rows, so we can say that you consider that the number of rows. The second bracket is the number of columns. So when we initialize this A to a new two-dimensional array of 3 and 4, that's 3 rows and 4 columns. You can use array literals just like we did with one-dimensional arrays. So you notice we have the outer bracket, we have a row here with the 4 values for the column, and then you have the second row, and then the third row with each of them have 4 elements in each column. So you now have created A, which has got 3 rows and 4 columns. We can also create additional dimensional arrays, 3 dimensions, which was another set of brackets, 4 dimensions with 4 sets of brackets, 5 dimensions, etc., etc. Three-dimensional arrays might be useful in something like modeling, a volume, or something like maybe in weather where you have different things at different locations at different altitudes. Maybe you do it for sort of mapping, space with altitude, or maybe underwater things. Once you get past 3 dimensions, that gets very complicated and is not used very often. We just, as people, don't have a natural sense of multiple dimensions beyond 3. So you probably wouldn't model it, but Java supports multiple dimensions. You just don't see it. We often see 2 dimensions or single dimensions, and rarely 3 dimensions when you're talking about volume. So how do we think about these two-dimensional arrays? We initialize our arrays with rows and columns. You can think of it as a matrix. It's very natural to think of it as a matrix, as a matrix with 3 rows, 4 columns. The things are there. We can refer to them in row and column. But under the hood, Java actually holds references. As you remember, the variable type A, or the variable A, is just a reference that points to the array. And actually A points to an array of 3 things that refer to arrays of length 4. So they're arrays of arrays. So that's what Java actually does, is Java says A is an array, so you can actually refer to A as an array. So you could actually refer to A as an array. You could actually initialize A as saying A is a new int with 3 rows, and the length of the columns are undetermined at this time. We can refer to A.length, which would return 3. We can actually refer to the first item in A, the second item in A, and the third item in A, and we can initialize them to different length arrays. So we create if A0 has a length of 1, A1 has a length of 2, A2 has a length of 3, we have created a triangular matrix that is a nice way of storing, or useful in storing, a symmetric matrix, as you read in the text. A symmetric matrix has a diagonal, and then the ones below the diagonal are mapped or rotated on top of the upper diagonal. So you can store a triangular matrix or a symmetric matrix by just storing either the lower half or the upper half of your matrix in the triangle, and Java happily supports that, and you're saving a lot of space because you only have to store half the information. Takes a little bit of getting used to, but you can actually now say A.length, which will tell you how many rows A has, and then you could say A0.length, which tells you how many columns rows 0 has, and how many columns row 1 has, and how many columns row 2 has. So you can always ask those questions of this two-dimensional array. So what would be some sort of uses or processing of two-dimensional arrays? The one the textbook talks about is classic 1970s game. It's a single-player game. It actually plays by itself, called Conway's Game of Life. It models a grid where each cell is either alive or dead, and each step there are simple rules to determine whether a cell, if it's alive, continues to live, or if it's dead, becomes alive. So it's reasonably simple. If a cell's alive in this step, it will be alive in the next step if it has 2 or 3 living neighbors. So if it doesn't have 2 or 3 living neighbors, it's either too lonely and dies, or it's too crowded and dies. If it has 2 or 3 living neighbors, it continues to be alive in the next step. If a cell is dead in this step and has 3 living neighbors, it becomes alive in the next step. So this very simple set of rules produces some very, very interesting patterns when you let the program run. The text has the code, so you can actually load up the code and run it and actually watch the patterns go by. We'll talk a little bit more about some of the code in the next couple steps, but first I want to talk about how things, if this were my grid, what happens. We see that the grid here only has 1 live neighbor, so it's dead in the next step. The cell here has 3 neighbors, so it's alive in the next step. So you see that a flat bar will become a vertical bar, which will become a flat bar, so we'll just switch back and forth. This cell has too many neighbors, so it dies, but then this cell has 3 neighbors, so it becomes alive. This cell becomes alive, so that's why you get the changes. The grid, the 4-block grid, is actually very stable because each of the cells here have 3 neighbors, so in the next step it will be alive, but there aren't 3 around, so it just stays a square. So you can see how you get some very interesting patterns. Things can move across the screen. There's lots of examples of this Conway's Game of Life. So let's talk a little bit about how you would actually do some of the coding. So you can represent the grid as a 2-dimensional array of Boolean. We're going to call it alive. If alive is true, then that cell is alive. If it's false, then the cell is dead. To initialize the grid, we just create a new Boolean array at this fixed grid size, so we're going to create a square grid. And then we need to initialize each of the individual cells. So we're going to loop over all the rows and all the columns, and then we're going to say alive row and column is equal to math random less than 25. So if the random number we pick from 0 to 0.99 is less than 0.25, then we're going to say it's alive, else it will be false. So we're going to only populate randomly 25% of each cell. Each cell has a 25% chance of being alive. So that's a random initialization for our grid. So now we have our grid, we want to talk about what's the logic for the next step. So we have our grid, we want to say what's the next step. So we need to create a new Boolean array of the same size as alive, because we need to populate this new Boolean array. So we loop over each row and each column, and then we count the number of live neighbors for each cell. If that number is 3, it's going to be alive, because the rule says if a cell is alive and it has 3 neighbors, it's alive. Or if a cell was dead and it has 3 neighbors, it's going to be alive. So if the number of neighbors is 3, we would know that we're going to make that cell alive. If it was dead before, it's going to be alive now. Or if it has 2 neighbors and it is alive in this step, we want it to continue to be alive. Else, everything else, all other combinations, you have 0 live neighbors, you have 1 live neighbor, you have 8 live neighbors, that will kill you. Too many neighbors, overcrowded. And then, so that will populate this new board. Once we've gone through every cell in the new board, we need to assign it to the live variable, and so that will update our board to the next step. So this is the logic for, we create the new array, we go through and calculate to see whether in which cells are still alive or which cells have died, and then we assign it back to our live array, two-dimensional array. So now, how do we count the live neighbors in a particular cell R and C, row and column? Well, we are worried about the row above, the row below, the column to the left, and the column to the right. So we have to look at those 8 cells. So it's alive R1 minus R minus 1, C minus 1, that's the upper left-hand corner, all the way. So you can see what the indices of the cells that I'm interested in, and I have to, if that is true, I increment the count. So the code looks something like this, but I have to worry about if that row is at 0, or the column is at 0, or the row is at the edge. We have to worry about the edges of the grid. So here's the logic for the, if we're just consider the edge as 0 grid, so we have to say if R minus 1 is greater than or equal to 0, then we're not at the edge. So that, and using the AND, make sure that if that is false, we stop executing the if statement. So if the C minus 1 is not greater than 0, greater than or equal to 0, I have a typo, and it's alive, we count it, right, we increment the number of neighbors because we're considering the row R and the column R. So if the upper left-hand neighbor is alive, we increment the count. If the next if statement again checks to see if we're at the edge. If the guy above us is alive, we increment the count, and then we say if the guy to the upper right is alive, we increment the count, and we check to see the grid. In the text, the author has a very nice way of making an assumption that says the left edge is connected to the right edge and the top edge is connected to the bottom edge, and that greatly simplifies your logic. You don't have all of these multiple conditions in your if statements. You just say if the upper left is alive, the upper center is alive, the upper right is alive, if the right center is alive, left center, right center, and then all the way around, and you count them up. It's a very nice way of simplifying the text. Also, I'm not going to go over it here, but the text has a checkers game where it's a fairly complicated program, but I'm not going to go over it, where he enforces the rules of checkers. Each square has a state associated to it. Is it a red piece, a black piece? Is it a red king? Is it a black king? And that determines how you can move your checkers. It's a good idea to take a look at his code and understand how he represents the checkerboard grid, and how he manages the playing pieces and where they are. So this is a brief overview of a two-dimensional grid. You can imagine if you wanted to do something with chess, you would have, again, you'd have to represent what each of the pieces on the thing, where it moves. If you want to do three-dimensional chess, you would add 3 dimensions. So you could see how this can rapidly get more complicated, but you still are, at the end of the day, using these arrays of arrays of arrays to represent your space. You can consider them a matrix, which is very nice when you're thinking about the problem. But remember, at the end of the day, Java is going to have your variable points to an array that holds references to other arrays, which may hold references to other arrays when you get further dimensionals. So thank you for your time.